How's it going, everyone? Welcome. Oliver Gonzalez here, and today let's going to explore now at what this pillar of JavaScript is all about. Thanks to Kyle Simpson, a software engineer that has previously worked to several companies. Also, he is the author of several books. One of them is You Don't Know GS and Functional Like JavaScript. So this is just, or in today's video, I'm going to now dive deep into what we really care about, that which is these three pillars that, based on Kyle Simpson, describe, right? One of them is the type system, and we're going through the primitive, the well, this course is organized like this, so we're gonna look at the type system, the primitive, as well as the coercion. If you take a look at this, so the primitive, the type of operators as a way to get now those particularly primitive values, some or the kind of emptiness here, especially when we talk about concepts like undefined, uninitialized, and so undefined, uninitialized, and on so undefined, uninitialized. Oh my God. So undefined, undeclared, and uninitialized, right? And then some special cases for this primitive, right? Such as the isNaN and the positive and negative zeros. And we also look at a particular example of how can we now determine is the type of value, especially for isNaN and positive and negative value. So the TLDR of that is for isNaN, since isNaN is a way of, or is a type of value that says, hey, this is not a valid representation of a number. And this is something that comes from, let me actually pull this up. I don't have it. I don't believe it. There you got it. Special values. It comes from the IEEE 754, which is this Institute of Electric and Electronic Engineering, where now they say, hey, we need to find a common ground to know how can we represent is numbers, right? So especially for floating point units. So this spec, all right, for floating points arithmetics, right, is a way of how you can define now this. So for example, arithmetic format, set of binary and decimal, floating point data, which consists of finite numbers, signed zeros or subnumber zeros, infinite, which is also a valid primitive or a valid type, and a special, not a number, values like this. So not a number, right? This particular standard that comes from this, again, you don't need to remember this or memorizing this, okay? But as you evolve as you evolve in your understanding of the pillar of JavaScript, all right? Because at the end of the day, we want to be competent and effective JavaScript developers. This is the only profession, I will say, that we are professional guessers. And if you are building if you're an architect defining all of the plans for a building, and somehow you guess what's going to happen when you put now a column here, so that will now fall down when the building is done and might kill a lot of people. So you don't want that. We don't want that. So because now the risk as a JavaScript developers, and I'm going to make a quick pause here because this is for real. The impact that we have now as engineer, somebody that uses the creativity plus the law of physics to actually build something with his ingenuity. Now there are a lot of stake, especially when we are going to build or develop this kind of application, because we don't see the impact right away, only when things go wrong. This is one of the things that JavaScript developer or any software developer, but I say JavaScript developers, because we feel that it all starts with games until your bank account is until your bank account hits zero, right? Until somebody steals your money. And we don't want to reach to that point. So because of that, and again, unfortunately, through history, we have learned that the best way we learn is through crisis. Why in the F do we need to put ourselves into that position if we know that it's likely to happen? This is a course for that. This is a course for myself and for those who wants to actually be genuine and act accordingly on this kind of topics. And when they need to handle the JavaScript, they see like as this as a tool that they need to manage, they need to will, all right, pretty much like a wrench, okay, that they can do several stuff, and those stuff can now have consequence to that. So because of that, right? So that's, at least I'm trying to now bring this a concept of the pillar of JavaScript, or the mechanism of JavaScript, which is the type system, the scope, and the objects orientated, all right? And I'm diving into this topic because it is important as a JavaScript developers, all right? So let's get into this. So this is why we look over this particular topic, okay? So again, in today's video, we're gonna look at coercion in some of the abstract operations, the too primitive to big int, too primitive to string to number, and to string to number, to boolean, to see how actually all of this different concept fits together. All right, but I need to, well, make a quick recap of what we went through all of this, right? So as I mentioned before, this particular course is laid out in these three pillars, right? The type system, scope, something that we're gonna see that later, and the objects oriented. So right now we're focused our attention on types, all right? We went through primitive type, which is something that we are quite familiar with, okay? And primitive type are atomic values that they cannot be decomposed, okay? So we have now is the undefined, null, number, strings, boolean, symbol, and wait, what? Exactly. So undefined, null, string, boolean, symbols, big int, all right? And this is the six, and this is the six. What did I mention? So I say undefined, null, boolean, string, number, symbol, and big int. Okay, so far there are 7 primitive, and then you have now objects. All right. So an object is a special type of that, which is a callable object. All right. That we also have now another special type of object, which is array, that has now an index and a property length. All right. So, but again, The idea is to, by recapping with typeof, which is the way of how can we now get the type of this value, because values are not in value. Variables doesn't hold, so type doesn't hold values, or exactly. So variables doesn't have types, values do, and this will be now the entry point for the next topic, which is, once we already know what is the type of this, okay, and some nuance, because when you try to get something or the type of a value, so for example, when you talk about null and stuff like that, right? For example, hey, I want to know what is the type of this, and tells you is now this is a function, or it can be an object, or is this an object, and not to mention is the big int, right? So when we play now with null or kind of emptiness, okay, this particular concept of undefined, undefined, undeclared, and uninitialized. So undefined is, well, you create this object, but it doesn't have any value assigned. Undeclared is that you didn't even create this, okay, value. And then uninitialized, which is now aka the temporal dead zone. So this is true for let and block scope variables, especially with let, all right, where they get initialized but never with undefined. Unlike var, they are declared with they are initialized is with undefined. This kind of state or emptiness is something that can happen, especially with let. But in any case, again, the idea of this is to explore now what is the. This is quite interesting that I didn't mention about the type null. I don't like this. I don't like this. I definitely don't like this. Okay. Really? Go on.
Our first list out function, if you look closely in that previous list, it didn't list out function, and yet we know intuitively that values which are functions have a very specific behavior that is different from values that are numbers, for example. So isn't it a type? JavaScript refers to functions essentially as a subtype of the object type. In fact, in certain places refers to them as callable objects. So it's sort of a type, but a subtype rather than a top-level type. Arrays, we use these all the time, and it seems like they definitely have a specific behavior. They're numerically indexed, and they have a length property that automatically updates, and they have various methods to them. So are they a type? Again, the best way to think about them, the best mental model I've come up with, is that it's a subtype of the object type. It's a special kind of object with this numeric indexing, a special kind of object that has this magical length property getter thing on it, okay? So it's not really a top-level type, but it's certainly a kind of value that has a certain kind of behavior, and it's useful for us to be able to distinguish. If we need to do something with an array and we have this value, we don't know if it's an array, we need to determine, is it an array? Speaking of determining, how are we going to determine all of these things? And I'm going to throw in a little forward-thinking stuff, because at the moment, this isn't actually in the spec, but it's like stage 3 and probably going to land in the spec, at least I hope soon, and that's finally that JavaScript's getting big int support, big integer support, large integer support. And when it does come to JavaScript, almost certainly when it lands in the language, it's going to be another primitive type. So it's on this list only because it's not actually here, but it's actually already implemented, for example, in V8. So in all of your Chrome-based environments, including Node, you have big int support. And it's likely going to land officially within the language. There is obviously a caveat that until it's there, it's not there. And things have been late stage 3, almost stage 4, and then been completely deleted. So I can't guarantee that there will be big ints, but it's pretty certain at this point. I'd say at least 95%. So these are some things that are values that we can expect certain characteristics from. And there's a critical detail that I don't want you to miss here, which is that most of these are not objects, right? These are objects, All of these, not objects. All of these may have, or at least many of these may have, object-like behaviors that you can opt into, but they are definitely not objects. Unlike languages like C++ and Java, in JavaScript and in other dynamically typed languages, it is not the variables that have types, it is the values themselves that have types. And that matches with that instinctual definition I just gave types, that they're the assumed or instinctual characteristics. And that's finally the...
Exactly, so far...
I think that's where a lot of people get confused. I mean, different value types. And that's finally that JavaScript's getting. And it does come to Java, actually here, so in all of support. There is all late state heuristics from it, right? These are objects, all of these, not objects. All of these may have, or at least many of these may have, object-like behaviors that you can opt into, but they are definitely not objects. Unlike languages like C++
I want to
and Java,
now,
in JavaScript and in other
up,
dynamically
right?
typed languages, it is not the variables that have types, it is the values themselves that have types. And that matches with that instinctual definition I just gave types, that they're the assumed or instinctual characteristics we expect from the values. Well, of course, let's refer to them then as value types. That's a better way of distinguishing it than to try to get the types police to jump all over us and tell us, no, these don't qualify as types. I've had that happen. I've had that argument many a time, okay? As far as I'm concerned, if JavaScript calls it a type, I think it's a type. When we assign some value to a variable, or in the case of line 1, haven't assigned anything and it sort of defaults, then we use an operator like typeof as our first way of looking at that value and determining something about its identity, its kind, its type. And we're not asking what's the type of the variable v, we're asking what is the type of the value that is currently in v. That's what line 2 says. What is the type of the value that's currently in v? And you'll notice that on line 2 it returns the string undefined. Now that's interesting because it has some value, and then it goes, then we've reduced the whole, we need further. You would use undefined, but if you wanted to unset an object reference, you would use null. And I think that's part of the historical reason for why type of null returns object. But
here, this is the historical reason. Okay, this is one of the tips here. All right, especially why when you now invoke v with null, it gives you now an object.
But if you wanted to unset an object,
which is here. Okay, this is type of operator. Okay, no, which is this, right? The type of operator. So far, so good with this, but here, when we define so we will define a variable and assign null, which is emptiness. It's like I create this space in memory, but it doesn't have anything in there, all right? So when you want to check the value or the type of this space in memory, whether it is a number or whether it's a number or a string or a Boolean symbol, which is a special ID that use now JavaScript to uniquely identify objects, something that go beyond the scope of today's video, so we mentioned is undefined, okay. So we mentioned undefined, which is say, hey, you didn't even create this, right? Undefined. Exactly, with undefined, right? It's like, hey, you undefine and undeclare. So you create this, but there is no value assigned to, all right? Whereas with null, you say, hey, you create this, but the value that is assigned is empty. You know, it's nothing. We need to represent emptiness here. So when you use, for example, with primitive, like undefined, which is good, and a string, and a number, and a Boolean, and an object, and a symbol, it works as expected, the type of. But when we want to now check things like kind of emptiness, all right, like v equal null, for example, you say, hey, I reserve a space in memory. Here, you can think of this as like this, right? So I reserve a space in memory to put only here is um, numbers or booleans or strings, big int, symbols, even undefined or objects, right? Any kind of objects. But here you have now in memory this particular slot here. So that slot that you let JavaScript to be assigned for you, all right? When you use now null, you're telling, hey, I want to this be like this. You know, it just wants to reserve a space in memory here, this region on the memory, so I can now add some stuff there at some point in the future. But right now, nothing. You know, free space, bro, free space, sister. And because the way how now, if you want to unset an object reference,
is undefined, but if you want
because
a regular value, like a number, which essentially indicated to developers that if you wanted to unset a regular value, like a number, you would use undefined, but if you wanted to unset an object reference, you would use null. And I think that's part of the historical reason for why type of null returns object. But the real truth of the matter, I was tweeting about this years back, and the real truth of the matter is that it's just a bug. It ought to have returned, quote, null, to tell us that this is a value of the type null. You'll notice that when we say type of v equals null, I'm sorry, when we say v equals null and type of v, we get back, quote, object. Now, this is...
And I think this is something to clarify this, okay? The type of v equal null. Exactly. So the type of null, and I want to make a special mention here, because I think it's quite important. Yeah, it is. Absolutely. Come on. So returning an object is there for historical reason, and the reason is that if you want to unset a value primitive in ex6 one, in other words, it's like, hey, I want to ditch the value that I hold here. Eh? So if I want to ditch the value that I hold here, all right, so whatever I say, hey, this is a number, right? But now I don't want to be this is a number anymore. I want to unset that. So if you unset a primitive value, you use undefined. But if you want to unset an object which is a reference in memory, you will use null. And this is might be the historical reason of why when you ask type of a null variable assigned to, give you now an object. Even though those things started to make a lot of sense. So even though it's just a bug, and we have to be careful when to use it. The TLDR of that is just like that, you know. And if we want to now check here, for example, some big int, right? You say, hey, big int. You can do something like this, or you can do something like this as well. And if you want to check the type of this, you say big int. Right? This is a way of how you can represent this values. My question is, what would be the use cases for big int? I was going to ask Claude for this, shall we? Oh, come on, Claude, for real? Okay. What is the main use case for big int? Right. High precision time step. Nanosecond. Oh, okay. Interesting. Interesting. Price in cents, right? And you want to calculate is the 8% of that. Cryptography based on exponent times modular and 64 bit timestamp. Can mix bit in with regular numbers. So I want to now take this and give me now the 8% of the tax calculation here. When precision is needed. So when precision is needed. Okay, cryptography. When precision is needed, when dealing with large monetary amount in the smallest currency unit, like working with cents instead of dollar to avoid floating point issues. Okay. To avoid point floating issues. So for example, you say it's not a valid number. Oh, because you want to use a full representation of this. So it's a full representation of this. Okay, it's a full representation of this. So for example, let's say 1000, all right, and then you assign this to some form, say a price, okay. So I'm reserving a space in memory for this price. And then I say, hey, I want to take is the 8% of this, all right, and divide by 100, n, big end, all right. And then also I want to assign that. So you're going to multiply this number by 8 and then divide by 100. To get is the 8%. But if I want to get 1%, is this. But to get the 8% is this. You say now, well, tax. And if you want to know what tax is, it say that this is 80 for that. But what if you say, for example, 0.5? That's the question here. Because if you want to represent now point floating numbers, how would you represent point floating numbers? You can't represent point floating number with big int. It only handles integers. That makes a lot. Okay. 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 For larger or high precision floating points, you have these options. You either handle that as a regular expression or manual fixed point arithmetic. most use cases, use regular number unless you specifically need arbitrary precision. Okay, but it's because big int is only to represent is big numbers, big integers. You know, how big? You know, how big integers is this? You know, so big bit int. You know, big int. That's right. How big it represents? Let me actually take a look at this big int. Gonna take a look at this spec, bro. Big int. See all possible big int values. Big int object. Member of the object. Big int type. Okay. The big int type represents an integer value. The value may be any size and it is not limited to a particular bit width. Generally, where not otherwise noted, operations are designed to return exact mathematically based answer. For binary operations, big int act as two complementary binary string, with negative number treated as having bits set infinitely to the left. Big int unity, big int wise, big int exponential. What is this? The methods. Big int reminder. Okay. So if we look at this, it must have is some sort of operation here. You have big int, the constructor as int, uint, instance methods. But what is this? Big int unity minus the abstract operation. Oh, and when you talk about abstract operations here, is okay. It makes a lot of sense. So these abstract operations are the way how the type conversions happen. Unity minus, big int bitwise not, exponential, multiply, and return a big int. This is part of the type system. Interesting. Even if the result has much larger bit width than the input, the exact mathematical answer is given. The exact mathematical answer is given. So in other words, if you do something like this, let's say, hey, let's going to multiply is 99 big int times 99 big int, all right, it's gonna give you now the mathematical number of this. So for example, you say this now in natural numbers times 99, it gives you that. But again, because this number has a finite representation, okay, 3, 6, 12, 24, 48, 96, 92. So instead of copying all of that, you can say is, hey, 1e plus 255, 256, 257. Interesting. Can you do 512? Infinite. Okay. Here is where I want to reach the limit of the natural numbers or the number type. Okay, so how much you can represent, how much here in this slot in memory you can represent, you can put here. So let's get into number. And you may wonder why you are looking into this. Bear with me. So this number here, most of the time we don't deal with that, you know. Number max safe integer. Here we are. You got it. So the instance of number tells you is what is the max safe integer value, or this one, max value, my safe integer, positive, and max value, right? What is the max value that you can represent here? So for example, if you say now 1.8 power to 30n, or you can say is this, it is true, right? Which means that this particular number, it will be expressed as infinite. You know, JavaScript evaluate this statement and say, hey, this is something that I cannot represent. However, I have something that can be used to represent that, and that is infinite. It's like you're trying to count until 20 gazillions. Yeah, gazillion actually is a word. Gazillion. Yep. And gazillion is a very large number of quantity. Okay, but I want to be more specific. All right. Or Basilian, gazillion. If we look now at the representation here, or let's say is memory size representation limits. All right. So here we say terabyte, exabyte, yottabyte. I think yottabyte is the most bigger one. Exactly. We reached to terabyte, okay? But also there are now yottabyte, which is 124 zettabytes, and zettabyte is 124 exabyte, and exabyte is 1024 petabytes, and so on and so forth, you know. So, but the point of this is the representations of this data that we can count. Most of us reach to trillion numbers. In Spanish, that's billion, billones, right? But we can even count that. So trillion of trillions, or trillion of trillions, so on and so forth. But this is so big, huge numbers that are now representing galactic stuff, galactic distance. Or it can represent is now galactic, or it can represent is quantum distance as well. You know, from the galactic, from the bigger to the smaller one. Again, I'm doing this because big int allow us to represent is 253 minus 1. So let me actually go to English here a little bit. There you go. Double precision binary form. There you get it. You know, it makes a lot of sense. So this IEEE 754 double precision binary float point format, okay, is interesting. Is a way of how we're going to represent this. All right. Sometimes we want to express now the exponent and the fraction, okay, which in our case, 1 bit for sign, positive or negative. And as you can see here, this is a standard that allows to represent is numbers. It's a technical standard for specifically for floating point arithmetic. Okay. And you might say, hey, this is quite boring. It's like, why do I need to learn to look at all of this? From the perspective of understanding, it is important and it is interesting because things started to make a lot of sense when you want to now work with integers. I'm looking right now is what is the maximum value that I can represent here. Max safe integer. Okay. What this value represents here, right? So the maximum safe integer that we can represent is 2 power to 53. Can we compute that because that number is so huge? 2 power 53. Can you bring that up in decimal? You know, you are saying here, white cloud is not open here, man. Okay, finally. It's I don't know why it's not working here, or it doesn't want to work here. Anyway, chill. 2 power 8 2 E53. Okay, so okay. Okay. 2 to the power base exponent. Okay, it's because it's this. Okay, exponential base exponential. Okay, it's not the same. Interesting. Okay, good. But it's this one. Okay. Okay, it's quite different. We can think of this. Like a 1 followed by 53 trailing zeros, right? Is 2 to the power of 53, which is 2 to the power of, oh no, exactly. Okay, it's 2 to the power of 53. Is 2 to the power of 53. Okay, so in decimal, 16. By 3, 6, 7, 8, 9, 9 digits. Ah, more 15 digits. Okay, 3 6 3 6 as quadrillion, a 16-digit number starting with 9. A 16-digit number starting a 16-digit number. Oh, okay. A 16-digit number starting with 9. Oh my god. Okay, okay. I think this is a 16 a 16 a 16 digit starting with 9. So you got now a 16 digit here. 3 6 7 9. So 16 digit total start with 9. Okay. So this is a 16 digit. If you imagine that most of the time we can count on to 6 digit is a million. 9 is a trillion. 12 is a trillion in Spanish. Now this is a 16. If 6 digit is a million, a 9 digits a billion, a 12 digits a trillion in US notation. Okay. What will it be? Exactly. So what would it be? 15 digit. It's like a quadrillion. Okay. It's like a quadrillion. Okay. Okay. So I'm going to oh, it actually opened. Good. It takes time. All right. So here we are. Now, why do we even care about this? So now that we know that the historical reference that anytime you check the type of a variable assigned to null give you an object, is because in EX1, when you want to unset a variable, a primitive value to null, well, you need to use undefined to do that. If you want to now unset an object reference, then you now have to use null. This is the reason why it actually, when you check the typeof with null, it gives you now an object. The thing here is that it doesn't matter. It's just a bug, bro. It's just a bug. And we need to be careful when you use null. The other, right, which is something that it doesn't mention too much, but it's quite important, is the big end. I want to make a quick note here with the big end. Okay. Yeah, I'm gonna make a quick note here with big end. It allows us to represent integers bigger than 16 digits. All right, something that number primitive which is exactly, which is the limit, which is the limit of, which is the limit of numerical representation, which might sound boring, but it's like, how do you represent? So imagine that you represent is the Yu-Gi-Oh cards for those who play Yu-Gi-Oh, right? Or dominoes. Anyone play dominoes or truco? Hmm? Or anytime you want to represent something like that, Pokemon cards, you know? So how do you represent all of that set, all of that collections here? Is that, okay, that's good, that's great. How do you do that? Exactly, you set now a limit to that. Anything that go beyond that, for simplicity, it doesn't exist. All right, or you can't represent because it's not feasible right now. Okay, so there is no use in those numbers. So it allows to represent integer bigger than 16 digits. Why doesn't it? It's like, what is the distance between here, Earth, and the planet called, and the next star called Alpha Centauri? You know? What is that? What is the distance between here and the nearest sun, solar system, Alpha Centauri? Is huge. Question, can we reach to there? No. So why we even think about it? It's interesting. It's interesting to think about it, all right? But right now there is few applicability. It doesn't mean that it doesn't exist, but for practicality, we say, all right, good, but this is the kind of problem that we need to solve. You know? All right, so it allows to represent integers bigger than 16 digits, which is the limit of numerical representation, representations from number primitive. Okay, that's what it is. Okay. Safely. Okay. 15 digits safely. Exactly. 15 digits safely. Interesting. 15 digits safely. So, if 6 digits is a million, 9 is a billion, 12 is a trillion, 15 is quadrillion, right? So any other number beyond that, good that it exists, good to know, bro, girl, but we don't care right now. We don't care right now. So, yeah, good. So, because of that, because now specifically 2 power 53 safe integers, right? That give you this a 9 follow a starting 9 followed by a 16 or 15 digits. That's what it is. Then 15 digits, which is the limit of say numerical representation for number primitive. Okay? by the able trickery 754. So good, so far so good. Exactly. Which is imposed by the Institute of Engineering, Electrical Engineering, Electrical and Electronic Engineering, 754 spec. Okay, so far so good. So now things makes a lot of sense. What we need to explain is this big int. All right, so that's great. So if you want to represent now 54, it tells you 55. What the French does? Power this 53, 54. Wait, what? Oh, exactly. But this is maximum integer safe with sign. Exactly, because this is maximum integer safe. You can say is this. It's a number max safe integer is this. If you say max plus 1, but it's something like that. Again, this is the maximum safe integer that you can represent. Okay, more than that, the consistency of the number or what you're going to store is not guaranteed. It's not guaranteed. And double precision number okay, see what every programmer needs to know about arithmetic of okay. Why don't my numbers add up? Oh, welcome. welcome. Or why don't my what every programmer should know about floating point arithmetic, or why don't my numbers add up? So you are reading some absurdly simple code for say like this. Here we go. 4.1 plus 4.2, and then it tells you this. And got a really unexpected result. Maybe you asked for help on some forums and got pointed to a long article with a lot of formula that didn't seem to help with your problem. Well, this site is here to explain consistently why you get that unexpected result, tells you how to deal with these problems, and if you're interested, provide a high in-depth explanation of why floating points numbers have to work like that and what other problems can arise. You should look at basic answers first, but don't stop there. Let me take a look at the basic answer, my friend. We all reach to this point is because we are now looking at the limits of how do we store data, specifically number representations in memory. Okay, so because of that, that might be like a fun fact here, but it's important to at least be able to describe why big int is useful here when you want to represent now precision with long numbers. Okay, and what is the problem that numbers doesn't what is the problem that number has, and what's the problem that, or what is the solution that big int comes here or brings to the table. So why don't my numbers like 1 plus like 01 and 02 add up to a nice round 03, and instead I get we result like this because internally computer use a format binary floating points that cannot accurately represent a number like 0.1 and 0.2 or 0.3 at all. Okay, so the problem is that they cannot represent is point floating or numbers, fractional numbers, accurately, like 0.1, 0.2, or 0.3 at all. It's interesting. When the code is compiled, or your interpreter, in this case JavaScript, your 0.1 is already rounded to the nearest number in that format, which result in a small rounding error. Okay, even before the calculation happens. So it takes now, okay, it's the way how now they are representing these numbers, and they cannot be represented accurately. So 1.1, what does it mean? You know, you can say that this is equal to 110, right? Quite interesting if you say something like this, right? But internally, it cannot represent accurately 0.41, 0.2, or 0.3 values. Holy crap. Okay. Since computer memory is limited, here we are. You cannot store numbers with infinite precision. We got it. Okay, cool. Cool up, absolutely. I totally get it, man. Okay. And it all starts with our limitations. So you cannot store numbers with infinite precision. So no matter whether you use binary fractions or decimal ones, at some point you have to cut off. Because you can represent that, let's say you do something like this. If you use a calculator and they say 1 times 10, it will give you 0.1, even though they are computing that, right? So if you, let me actually do this, you know. If for some reason we want to divide this, say 1 divided by 10, right? And then we say, well, because this cannot be represented like this, we take something, we add now here, and on the coefficient we say this, and as you can see, 10 out of 10 is actually, well, 1, right? Which is good. The other is 2, all right? Out of 10, and then you say, well, if you add now a 10 to this, you say this is 2, all right, and the other is now well, 30. You say something like this. But the thing here is that the floating point guy here is that to an engineer building a highway, it doesn't matter whether it is 10 meter or 10,000.1 meters wide. Their measurements are probably not that accurate in the first place. To someone designing a microchip, 0.0001 meters, a tenth of millimeter is a huge difference. But they will never have to deal with distance larger than 0.1 meters. A physicist needs to use the speed of light, which is 300 million and Newton's gravitational constant together in the same calculation. Larger numbers and small numbers. To certify the engineering and the chip designer, a number format has to provide accuracy for numbers at various different magnitudes. However, Only relative accuracy is needed. To satisfy the physicists, it must be possible to do calculations that involve numbers with different magnitudes. Basically, having a mixed number of integer and fractional digits is not useful, and the solution is a format with a floating point. Exponent and significant and exponent and the standard here. They are separate positive and negative zeros, positive and negative infinite, and not a number. So the thing here is that is because operations is because whether it's a compile or interpreted programming language or computer, because our memory is limited, we can represent accurately is 0.1, 0.2, and 0.3. So we have to now round that, which result in a small rounding error, even before the calculation happens. Why do computers use such a stupid system? It's not stupid, just different. Decimal number cannot accurately represent a number like 1/3. So you have to round to something like I did that wrong. I did that wrong. It's this. Exactly. Or this. Or 1. Or for example this. Exactly. When you need to, exactly. And it's because you want to represent how much is 1 divided by 3, which is 0.3.3.3.3. You get it? So because memory is our limit, so we need to round that as. We need to round that French toast stuff. So we round that, and that's the reason why it gave us now this funny error here. All right, so how can we now solve this? By wrapping this into a floor. All right, something like this. Or you say, hey, give me now is the round. Boop, boop, boop. Coercion. Exactly. Okay. Decimal numbers cannot accurately represent exactly our system. Our decimal system cannot accurately represent its numbers like 1 divided by 3. So you have to round to something like 0.333, and don't expect 0.333 to add up 1. Either do you. Computers use binary numbers because they are faster at dealing with those, and because for most calculation, a tiny error of centesimal decimal place doesn't matter at all, since the numbers you work with aren't round or that precise anyway. What can I do to avoid this problem? That depends on what kind of calculations you are doing. If you really need your result to add exactly, especially when you work with money, use a special decimal data type. If you don't want to see all of those extra decimals, simply format your result rounded to a fixed number placed when displaying it. So you say, hey, I want to now say math fix, math floor, or math round. No, because it round to that. You can say, hey, I want to transform this into a string by saying, hey, string. All right, and then now give me is let's gonna do something like this. say I want to transform this into a number. Okay, give me this number, and I want to now get is the 2 digits, you know, something like this. Okay, come on. Exactly. So you can do something like this. Try to be much more accurate here to represent that and transform that to only get this to decimals. So what other calculations like 0.1 or 0 work correctly? In that case, the result of 0.4 can represent exactly, but it's about its representation. And I think this is a very fun fact. I'll be right back. So now that you're dealing is with the limitations of the language. The limitations of the language. The limitations of the language. Okay, so we get it. So we get it, right? So we get it. Okay, so this is big in, all right? So big in allows to represent integers bigger than 15 digits, which is the max safe limit of what the number type allows to represent, okay, or 2 power to 53. So it is starting with a 9 followed by a 15 digits, which is enforced or imposed by the IEEE 754 spec. Good, good. So because, and I think this is quite like interesting to know about this, you know. Okay, so because, okay, we have a, because because memory is limited, right? Right now we have this old fancy way of storing data. You know, you have a huge amount of resources, but because even though memory is limited, because memory is limited, okay, as I mentioned here, okay, so since computer, or because computer memory is limited and represent 0. And represent 0.3 in decimal is not precise, aka So try to divide 1 3. Okay. Now, and see how many digits you can get. Okay. Numeric representations like point floating, okay, a binary floating points, right? Numeric representations like binary floating points, okay, and it accurately represents that. So binary representations or binary floating point cannot accurately represent that number. So computers internally, so computers or whatever language you use, whether it's an interpreter or not, okay, so when the code is compiled, so computers, when the code is compiled or interpreted, it rounds the value here, right? It's already rounded to the nearest number in that format. It rounded to the nearest value here. So we went through describe topics that are for a lot of times fun facts from JavaScript interviews. Okay, for example, it's like, what is the type of null? Right? And why it actually give it to do that? I think this kind of question actually reveal the seniority of a JavaScript developer, right? Or this one as well. It reveals how professional and how sincere is that person to dedicate, to devote his times to learn and to understand this kind of stuff. So I think that'll be all for this video. And I'm going to make this quick recap about this. All right, as a way to now give shape to this. Well, and at the end of the day, type is part of the pillar of JavaScript. So we first look at the primitive. What are the primitive? So undefined, null, Boolean string numbers, symbol, and big int. This recently added, not that recent. Okay, and also also something that is not a primitive, which is objects. Okay, and how now objects can represent several stuff. But in any case, the base is an object. And how when you check now with the type of operator, the entire different types that you can get, this finite set of values. First we'll look at the primitive, so far so good. When we explore about the undefined, no problem. But when it's null, it returns now an object. And this is for historical reasons. Because if you want, on the ES1, if you want to unset a value, if you want to unset a primitive value, you do a undefined, right? But if you want to unset an object, you do a null. So that's why it might return, that's why it's return you an object. In any case, this is a bug, bro. This is a bug, and you have to be careful with that, because if they don't want to break, so they don't want to change that, because otherwise it will break the entire internet and a huge economy. No, no. that's that's a no-no. This is one, and the other is now the big int. All right, what is the problem that big int aims to solve? Because these numeric representations with this primitive number, it only reached to 2 power to 53, which means that you can represent is now a 9, a digit starting by 9, followed by 15 digits. Okay, so if 6 digit is a million, 9 digit is a billion, 12 digit is a trillion, so here we're talking about now a quadrillion, right? So this is the amount of safe representation you can store, right? Sometimes it can go beyond the scope of that. What the fuck is this? So this is why. So now big int is a way to say, hey, we want to now represent is long integers to be much more accurate with that. So for example, it's like in the finance world or in the physics or the mathematics or in the cryptography as well. This is the main use case for this. And well, it also to look up the 0.1 and the 0. Plus 0.2 is equal to 0.3, and why it doesn't give you now the 0.3 completely, because since computer memory is limit and represent 0.3 in decimal is not accurate, so try to divide 1 times 3, all right, and see how many digits you can get from. We can think of this, right, as a way to try to force our brains to think. 1 divided by 3, all right, so again, so you need to add now a 0, all right, so now you're going to divide is 10, so you're going to divide is 3 by 10. So what is the closest number you can get? Well, 3. So 3 times 3 is 9, right? It's close to that, but it gives you now a 1 of model. So we need to continue to this operation is not end. We need to do that. So if we now add another 3, all right, so we represent is 3 times 3 is now 9, but it gives you now another is 1, and so on and so on and so forth. And because this number is so big, so huge, so we cannot represent accurately the and that's to me quite interesting. We cannot represent accurately is this in a decimal system. So what does in the binary floating point system is say, hey, I'm going to round this number, all right, at the computer, right? Whether if you're in a compiler or integrator or in a interpreter language, I'm gonna get that and I'm going to round that to the nearest element or to the nearest value, and I don't care. So how you can solve this? All right, that's a very good question. That's a very valid question. How you can solve this? Let me. As I mentioned here, to fix, right? The other is use epsilon for comparison. Convert to integers, multiple, calculate, and divide. We can also use arithmetic library. Exactly. So round to fixed decimal places is like this. So you get the idea. So this is how you can try to solve this. I don't think I have that. Right. Something like this. So yeah, so we now demystify something there, right? And then we talk about now the kind of emptiness, which is the undefined, undeclared, and uninitialized. Undefined is say, hey, you create the value, but it doesn't have any value. The undefined is say, hey, you didn't even create the value. And the undeclared and uninitialized, that this is for block scope variables like let, to say when you initialize a variable, we're not gonna put undefined when we use unlike var, for example. And that's good. That's great. That's huge, by the way. And then we deal with this special kind of values, such as the isName, positive or negative zeros, and when can we use them, all right? And what now isName actually represent, and how can we now check if the isName is correct? Because we have, for example, is several representation of that. For example, number is nan, which is to check if that particular nan is a number. At the end of the day, isnan says that this is not a valid representation of the IEEE 7454 spec, which means is, hey, this is not a valid representation of a number. I'm sorry, our memory is a limit. Deal with it. The computer's memory is limited. Deal with it, right? So isnan is the only value that is not equal to itself. And we can use that as a way to check that, right? In other words, like true, if you use now double equal or triple equals, is of course true. But if you use now isnan, it's not triple equal to itself, right? But again, it's a number at the end of the day. So the TLDR of that is use now is the isnan to check if they are different. That's the only way of how you can guarantee that, hey, if this num is an n, if it is, or if it gives you now it is n, let's going to see if they're different types. If it is, then you actually can guarantee and verify that this is an n. All right, and the other is -0, all right? To see how that works, all right? And the thing here is that with -0, anytime that you need to represent is now movement, all right, in a game or in a financial trading app, say the value is increasing or decreasing at real time. So you use now an object.is. I call this like the quadruple equals, all right? That actually verify that it is. So the sign value here is used in the industry to solve directions problem. And then we went through a particular example for that, which is kind of cool, you know, interesting. And then some fundamental objects, all right? Which is this built-in objects in the type that we use with new and we don't use with new. So anything that we don't use with new is the string, boolean, and number. but the rest we do. So for example, map, set, objects, array, date, booleans you don't use new with math, for example. And then we talk about now the coercion, or these abstract operations. Okay, so this is the building block operation that makes how we deal with type coercion. We actually look at the spec, we dive deep a little bit of what is this. Okay, so these abstract operations perform this type conversion. The type conversion in JavaScript, of course. I think that might be quite redundant, but I don't take anything for granted. Exactly. Exactly. And when you understand this, is like it makes a lot of sense. To primitive, convert object to primitive, to number to strings, and to boolean. So key abstract operations here. Key abstract operations here. Is this one. Convert objects to primitive. Okay. Something that we're going to now take a look at that, and it gave you this. The other is to number. Wait, what? Okay, give me like this, bro. Exactly. To primitive, which is converts objects to primitive, to numbers, to string, all right, and the to boolean, bro. All right, something that we're going to see that later on, but that'll be all for this video. Take care. Bye bye.